On for, I guess, 3 years now, enrolled in at least AP physics, capstone physics. And in class, I've known him to be quiet, but constantly always at the top of the class with everyone else there. It's really nice to see his confidence grow over the years and, working these difficult problems and getting the solution before others and kind of like, wow, okay, I did it. Yeah, you actually can. You have that ability to do that. Yeah, you are that good. So it's really nice to see that. Sean is an AP Scholar with Distinction. He's been the Math Student of the Year at BASIS and will be attending Brigham Young University. Sean.
Thank you everyone for coming out. As Mr. Lee said, my name is Sean Moss. I did an internship. I wasn't like Soraya where I kind of did my own thing. I interned at an architecture and engineering firm in town called GLHN. A little bit about my internship. My advisor is Mr. Henry Johnstone. He is the president and director of mechanical engineering at GLHN. It's located at Broadway and Country Club. I went down there 3 days a week, and what I did was I studied this. This is a very complex diagram, but I love it because it illustrates exactly how difficult what I was looking into, how difficult it really is and how many different aspects it has to it. I'm going to get deeper into this where this will start to make a little more sense. Before I could start to understand that, I had to get a lot of background information. Three main sources that I had. One was a water plan from City of Tucson Water from 2012. It talked about where Tucson gets its water and how it uses its water. Another was a 2014 Integrated Resource Plan from Tucson Electric Power. This one was really interesting in how it talks about how everywhere in how we get our power here in Tucson, where the power plants are located, what our fuel sources are, and just how much, how massive all of the steps and all of the actions taken to make sure that we have a reliable power source. And possibly the most important thing that I read was the Water Energy Nexus. It's a report published by the Department of Energy, and it really captures what I was studying, which was the Water Energy Nexus, which is a look into how water and energy combine, how they're intertwined, and how they're constant, and how each requires the other in order for the other one to be provided for us. That's really hard. I'll get into it. It's hard to explain without a lot of background. But essentially what I did down there is I worked with Mr. Johnstone, and I used Prezi, which is what I'm using now. It's a lot like PowerPoint, but it helps organize your ideas a little better. And I helped him make presentations that he gave at multiple events. He gave one for the Arizona Society for Heating, Refrigeration, and Air Conditioning Engineers, ASHRAE, the Tucson chapter. That was an hour-long presentation where he tied the water and energy nexus and how each of them are tied together into air conditioning and how some air conditioners use water, some air conditioners purely use energy, and how it's kind of an interesting balance between the ones that use water use less energy, but that water could have been used for other sources, such as creating the energy. Also energy efficiency workshops hosted by the mayor's office at the TEP Center downtown. Rocky Mountain Association, which was about college campuses and air conditioning in the Rocky Mountain states, Wyoming and Montana, all the way down to Arizona. And also similar workshops at the University of Arizona and Pima Community College about air conditioning and efficiency at college campuses. Okay, so now getting into the water energy nexus. This is kind of how I envision it in my mind, where there's two parts. On the top we have energy for water, and on the bottom we have water for energy. And they're really two separate things, but it's interesting to see how they combine and in some places collide to really cause problems. So first let's look into energy for water. There's really three main areas where this happens. The first is water treatment. When treating water, it actually occurs twice. Once before it even gets to our house or in our bathrooms and anywhere we go. It has to be treated to get some of the impurities out from the river or the reservoir or wherever we drew it from. And after use treatment requires a lot more energy to remove the solids and other waste products after we use it in our bathrooms, in our hand sinks, in our toilets. Water heating consumes about 25% of household energy if it's an electric water heater, which is a very big chunk of the pie when you think about it. 25% of all the energy used in your house is just to heat water so you can take a shower every day. And there's been estimates where you see that saving 1,000 gallons of hot water can save between 60 and 210 kilowatt hours a year. And that's a large amount of energy, especially when you consider that compared to 1,000 gallons of unheated water, it only would save about 3 to 5 kilowatt hours a year. Probably the biggest amount of energy put into getting water here is transportation of water to us in our houses. Aqueducts are used a lot in the West to transport water to the big cities like LA and Denver, Phoenix, Tucson, and one of Tucson's largest sources of water is the Central Arizona Project, which takes water from Lake Havasu on the Colorado River and transports it 300 miles through Phoenix down into Tucson. And this consumes 2.8 million megawatt hours annually. And that's a huge amount of water, especially when you think about if we can conserve water and we didn't pull as much water from Lake Havasu, how much energy could we save? This is a picture of the Colorado Basin. You can see there's a thin purple line here that is the Central Arizona Project. But you also see these red areas, and those are also areas where water is transported out of this Colorado Basin area into other basins that requires a lot of energy to get water to cities such as LA and San Diego, Albuquerque, Santa Fe, Salt Lake City, Denver. All of these rely on water from the Colorado Basin, and they're not even in the Colorado Basin. This is a really interesting picture that shows the elevation profile of the Central Arizona Project, which is how we get a lot of our water. And over the course of the length of over 300 miles of the Central Arizona Project, the water is vertically raised 2,900 feet in the air to get it over the mountains and to eventually flow all the way into the reservoirs and into the recharge areas to eventually be used in our homes. And that's another huge reason why so much energy is required just to get our water here in order for us to use in our everyday lives. So that's the energy for water. And so now we're going to look into water for energy, which is a little bit more substantial. Probably the biggest, it's really alarming when you look at these numbers. 50% of water withdrawals in the United States, about 50%, it's actually 49%, but about 50% are allocated directly to producing electrical power. And when I was studying these things at GLHN at my desk, I was, wow, you don't ever think of that. You don't think that 200 million gallons a day are used just so that we can have power in our homes to light our office buildings and things like that. You think it'd be for irrigation or our own personal use. But when you look at it, irrigation is only 31% of the water we use to grow crops and to feed ourselves. And the public supply is only 11%, which is, those two combined are still almost 10% less than the water we use just for providing electricity. And that was really shocking to me when I was looking at this, and I didn't realize, I always thought, wow, that if we could find better ways to grow food, or if we could conserve water, then that would be great. But really, if we find better ways to produce electricity, or smarter ways to produce electricity, that is where the real water savings lie. This is a figure that shows different fuel types and their water consumption. Coal is actually the most popular in the United States at 46%. And what's interesting here is that a lot of the fuels that we consider to be clean energy, because they have low carbon emissions, low sulfide emissions, that don't pollute the air, they actually use more water. Things such as biodiesels, such as nuclear power, they use more water, and it's interesting to think, there's always that big push toward clean energy, but when are we going to start seeing this other push toward less water-intensive energy? This is a breakdown of power generation in the United States. Again, 45% is coal, 24%, the next highest, is natural gas, and this has a lot to do with the recent boom in natural gas fracking and natural gas from shale, and 20% is nuclear. And what's also interesting is that hydropower, which is 6%, is usually thought to be very, very, very clean. It has absolutely no emissions into our atmosphere. But it actually, when you look at the numbers, it uses more water. And this is because when you dam it up to create the reservoir, you increase the surface area of the water that is being hit by the sun, causing even more of that water to evaporate and to be lost in the river. And over time, it's estimated that millions, even billions of gallons a year are lost in the Colorado River alone just due to evaporation because of the dams that we have set up to provide hydropower and to provide reservoirs. Also, another reason why so much water is needed is because we have very inefficient methods to produce energy. This is a Sankey diagram where the thickness of the line represents the amount of energy that goes towards it. At this point, we have the total energy in the system from the coal or from the natural gas. And at the end, this is what actually gets converted into electric power. That's only about a third. The most efficient coal plants can maybe reach 40%. Combined cycle gas plants are at about 50%, but we're losing a lot of energy because of all the water we need to provide electric power to cool the steam after it runs to the turbines. And so now we see how there's energy going towards water and water going towards energy, and it's interesting to see where these two collide in the middle. I'm going to take you back to this diagram once again. It probably should make a little bit more sense now. On the bottom we have the water, and on the top we have energy. And as you can see, there's water going up into the energy side, there's energy coming down into the water side, because they're so dependent on each other to provide a constant and ready supply for us in our everyday lives. And because of this, there's collisions happening all over the world. This is a water projection for Tucson, and based on different amounts of water consumption per capita, how much water we use and how much water we conserve, it doesn't look too good. Eventually, we're going to be running out of water by 2050. And that's a scary thought. But it's not just Tucson. This is a similar graphic for the entire Colorado Basin, where eventually the red shaded area of our demand will eventually outgrow the water supply in the blue area. And this isn't just the United States, this is the entire world. Australia and Qatar, they have very limited water supplies, and so it's very, very hard for them to provide enough water to produce the electricity. In France, they've had a lot of problems with their nuclear power plants. Water has been too hot when coming into the power plant, and it's not at the right temperature to be able to cool down the steam after it's run through the turbine, causing them to scale back on production and in some cases cause blackouts. Also, China and India, they also have very limited water tables because of how much water they're pulling out of the ground to provide electricity. India especially, they have very inefficient coal plants that require a lot of water, and they don't even have their entire population supplied with electricity yet. And if you look in the years to come, there's going to be a population increase, which will be, our estimated population by the year 2050 will be 9 billion people on this earth. And that will, in turn, by 2035, cause a 35% increase in energy usage. And in the same time period, because of the increased food, the increased usage by each of the people, and the increased energy usage, it'll cause an 85% increase in water usage. And we're already having a tough time finding enough water now. So just in the next 20 years, it's going to be really, really hard to find all the water that we need. And so you look at this, and I was looking at it, and I didn't, you got to find something that'll work. So part of my research, I also, after I finally kind of understood this and kind of could connect the pieces as to all the problems that there are and what needed to be done, we needed to be saving water to provide enough electricity and to provide for the people of the earth. The most prominent solution that I could find was solar power. This is a utility scale solar plant that is in Eastern California. It covers about 10 acres, a little bit less, and it provides 500 megawatts of electricity. At peak demand in Tucson, we have about 2,500 megawatts. So in just 10 acres, they provide about a fifth of what Tucson needs for its entire city. And so if we had about 50 acres or 60 of solar panels, we would be able to provide the electricity necessary for all of Tucson. And that's a small amount of land that is needed in order to provide electricity in a very water efficient way. It's also a great idea because the price of solar panels has been drastically decreasing. It's to just around 35 cents per watt for each for solar cells. Also, Arizona in particular has a great solar potential. As you may be able to tell, it's pretty sunny here all the time. Not today, but most of the time it's really, really sunny. And so with just solar panels, we could be providing electricity in a very clean way for everyone around here. And it doesn't just have to be in Arizona. This building is in Seattle. It's called the Bullitt Center. And you think Seattle, why would they use solar panels in Seattle? It's not very sunny. It rains all the time, so solar panels wouldn't make sense. But this building, with just the solar panels on its roof, produces enough electricity over the course of the year to compensate for all of the internal electricity use. This is also due to a lot of efficiency in the building. They have very efficient windows, they have efficient insulation, they have a complex computer system inside that opens windows at appropriate times to cool the building naturally. They use a lot of sunlight so that overhead lighting, electrical lighting isn't necessary. And probably one of the coolest things, I think, is their elevator, when it's going down, it uses the brakes actually produce electricity to slow it down, so that most of the energy, not all, but most of the energy for the elevator is produced by the elevator itself. Thanks again for all of you guys coming out. Thanks to Mr. Lee for being my advisor, and Mr. Johnstone for offering me this opportunity. Are there any questions? Mr. Hughes.
I want to thank you, first of all, for choosing this topic for your research project. I think these are some of the most important problems that our modern society faces. My question is about the use of water for power generation. and things like fossil fuel plants or nuclear plants. You mentioned that there's a great deal of water use for cooling the condenser so you can keep condensing steam and run your primary loop in the power plant. But doesn't that water go back into whatever source it was taken from after it cools your condenser? Does it end up back in the ocean, back in the river, back in the lake?
Yes, there's actually kind of two systems. That's used primarily in the east, where there's a lot of rivers, a lot of lakes, a lot of ponds that they can use. In the west, they have it on a closed loop, where they just evaporate the heat off through the steam and then recharge it with outside water. But each use consume water and it's lost to the system. After it's put back into the stream or into the lake, it comes out at a higher temperature, which increases the rate of evaporation of the water, causing more water to be lost than normally would.
Talking about using the benefits of solar energy, what gets us from where we are to there? And there must be big hurdles to get over. And what would those be?
Yes, there are. There's a lot of. First, you need to have the capacity to produce all those solar panels. Most solar panels only actually have a lifespan of around 20-25 years, so you need to be continuously producing them. Maintaining them as well would be a lot of struggle. You know, you have to clean them every once in a while to ensure that they're producing at their maximum efficiency. But power companies offer rebates for residential, and also for the utility scale. That's really up to power companies and them choosing where they get their power. You know, other businesses can just decide to build a large solar plant and then sell the electricity. There's a lot of different ways it can happen, and there's no real clear path to getting that.
So, utility-wise, they're waiting for another generation that will be more interested, a lot more interested in doing that? Is that
Yeah.
just old thinking versus new thinking?
Yeah, it's a long road to that opportunity. You know, it's not going to be cheap. It's going to be pricey. But if the options are pay more for electricity and have water rather than cheap electricity and no water, I would rather have water.
We're waiting for them.
Do you see the role of regulations to be promoting solar power?
Yeah, I know when we went to the meeting, it was an energy efficiency meeting at TEP. There was a lot of talk about rebates offered by Tucson Electric Power, and they're not the only ones. All around the country, power companies offer rebates to businesses or homeowners that invest into solar power to power their homes or their business or whatever, to try and kickstart getting more and more people on board with solar power.
You mentioned all the costs associated with solar power. Does it end up breaking even or costing more? Because it is cheaper power, but it's a lot of maintenance.
I'm not actually entirely sure about that. I know that with just straight solar panels, it would cost a little bit more than what we have now, because the process to make the solar cells is not cheap. It takes a lot of man hours, quite a bit of power to do that. But in the long run, it would cost more to pay for electricity from solar panels.
How do you propose to light my living room with solar power at night?
That's also very interesting. There's a lot of research into battery backups, to where most solar panels, they actually produce more power than is needed during the middle of the day. And so they can, if you divert that power that is unused into a battery, you can use that during the night. The problem is we don't really have the greatest batteries yet. So most of the time what people do is if they have solar power, they sell the excess electricity back into the grid. And so the power company buys that electricity from them to put back into other homes.
I seem to notice in the news lately, there's discussions, especially in California, it seems to be the topic of how much water almonds use. And then there's an argument, well, beef actually uses more, et cetera. And I never hear, your early graph really astounded me that that's all sort of a moot point when power generation should be a topic discussed. Or do you have any notion or idea as to why that is not entering the dialogue? Or maybe I'm just missing that.
I don't really know why the talk about how we produce our food is coming up so much more. What's actually interesting, I focused on just water and energy together, but a lot of times if you just search water energy nexus on the web, it'll actually come up with water energy food nexus, where it talks about how water is being split in massive amounts between both of them, and how both of them are just going to be increasing more food for the population, more power for our population, and how we need to find ways to gain efficiency in both. So a lot of times they're combined as sort of a triad of things that kind of have a pulley system where they're trying to pull from each other, and each needs its resources. But I guess food has kind of been the topic for a little bit longer, and it's kind of more recent where we're seeing this problem with electricity, because it's been recent that we've kind of been developing better technologies that use less water for our power production.
With all of this knowledge that you've gleaned and all the meetings and the people you've met, all the meetings you've sat through, do you come out of this more discouraged or more hopeful? Like, did you see any real innovative thinking, people really trying to dig into, I mean, we just sit around and wait for the next generation to come along and make the next step forward? Or is there movement on this?
You definitely see a lot of push towards energy efficiency. There's a lot of push towards saving power in businesses and in homes. There isn't, and that in turn saves water as well. But you don't really see a great deal of push towards changing the entire grid and where we get all of our power from to try and to really cut back on the water use. But this is something that's kind of recent, and it's definitely picking up steam. There's workshops being held all over the world for it, and I only assume that it will gain more steam and more people will start to hear about it.
That bullet building?
The Bullet Center?
Yeah. The bottom, the heating system of the floor, I didn't finish reading that.
Oh, it's a geothermal system. That's also a way that they save energy. It's cool because during the summer, the ground is cooler than the building.
Mm-hmm.
So they have water pipes that run through the floors and through some of the walls that cool the building. And during the winter, the ground is warmer, and so they can use that heat and heat the water, take heat from the ground, and distribute it through the building.
And through the water pipes along the walls and that's
Yeah,
how you
yeah.
inside the place.
Just a question. I know conservation is the best way, but we put a lot of money into finding new energy resources like oil and gas. Is anybody putting more time or knowledge into creating more water, like desalination or other things that we can increase that resource?
Desalination is an option. It's used widely in the Middle East, like Qatar and Dubai. They use desalination a lot. The problem with desalination is that it uses a lot of energy. So the energy needed to produce the water means we just need more water to produce more energy.
Has anybody looked into new ways of doing that, or is that
Um,
not an
there's-
area that they're
There was a few things that I saw. It wasn't very widely used, but think back the Sankey where I described how only about a third of the energy of the total energy in the fuel is used, and the rest is lost to heat energy. There's ideas where that heat energy can be used to desalinate water. It's not very efficient yet. It's kind of in the beginning stages, but they've definitely shown some promise with being able to do that.
Did you also, I'm so sorry, go ahead.
Did you also get a sense about, I mean, you were talking about the push for things like conservation and efficiency. Did you also get a sense of the political push against from, let's say, the coal industry and all the different players, all the stakeholders who are currently
Yeah.
making a lot of money
Yeah.
and are set to lose money
Yeah.
if
There's
you
def-
change things?
Yeah, there's definitely a lot of debate with coal and how it's it's really inefficient. It's a huge industry that provides jobs for a lot of people in America, and it's going to be hard to find a balance so that we don't just all of a sudden take jobs away from these people and take away a livelihood that they've had for generations in their small coal mining facilities. But it's just hard to find a balance because you don't want to completely take away everything, all of their livelihood, just so that we can have a more prosperous future, but we also need to make sure that we're providing for the future generations.
And why couldn't there be jobs created in the solar panel industry every place?
That's a lot of the idea, if we take away from one, add to another, and try and provide jobs for those that were lost and give it in another area.
And I was curious about the melting icebergs. We're running out of water, but then again, we've got all this water, all these oceans that are rising and losing their saltiness and so on due to, I wonder if all these merge. You talked about this.
There's a little bit of crossover, but not too much when looking at the big picture.